Hello everyone, welcome to my medical statistics class. I'm Kin from Department of Statistics, School of Public Health. Today we will go on to learn the method of chi-square test. So the first one, let's review what we have learned last class. Last class we have talked about some basic definitions which we used in chi-square test. For example, we have mentioned that chi-square test is a method of hypothesis test which is used for categorical data, and we often list all the numbers or the data in the form of a R times C contingency table. So there will be R rows and C columns in the table, and we said that we usually use the grouping variable as the rows. So that means there will be R groups in the research, and we use the effectiveness of the results of the treatment as the column variable. So that means there will be C levels under the column variable. But in a contingency table, there still will be some totals, the row totals and the column totals. And we have mentioned that the chi-square test actually is used to identify the difference between observed frequency and expected frequency. Last class we stopped here. We explain how can we get the expected frequency. We use E to represent the expected frequency, and we can find that the expected frequency equals to the cells row total times its corresponding column total divided by the total sample size, the little n. And we said that the little n is the summation of all the numbers in the R times C contingency table. Okay, so now let's learn something new. In chi-square test, we use chi-square value to be the test statistic. So we need to calculate the test statistic that focuses on the discrepancy between the observed and the expected frequencies in each cell of the table. If the overall discrepancy is large, then it's unlikely the null hypothesis is true. We have mentioned that the null hypothesis is there is no significantly difference of the column variable among different groups. So if the discrepancy between the observed and expected frequency is large, that means the null hypothesis is not true. We need to reject the null hypothesis. I think we have explained that last week. So given a R times C contingency table of observed and expected frequencies, where no expected frequency is less than 1 and no more than 20% of the expected frequencies are less than 5, then we will find that the test statistic chi-square value equals to this part. So this is actually the formula for chi-square value. But you may notice that I have mentioned some preconditions for this formula. That is what we found in mathematics. So you do need to know why, but you need to remember these preconditions. And I repeat it again. This formula is used when the expected frequency for each cell is bigger than 5. And actually there is another precondition, that is the total sample size, the little n, is more than or equal to 40. So under these two preconditions, you can use the formula. But if either of the two preconditions is not met, we need to correct the precondition. We need to correct the formula. So that means we have another formula, which is the corrected formula, the correction formula. I will show you later. Here we said that this value equals to chi-square, and this value follows a special distribution. We call it chi-square distribution. And similar ways what happened in T distribution. Chi-square distribution needs a df, degree of freedom. So this is the formula to calculate the df in chi-square distribution. And we can find that the df actually equals to r minus 1 times c minus 1. Here r means the number of rows in the r times c contingency table, and c means c columns. So actually we mean that r means there are r groups in the research and c levels under the column variable in the research. So this is the degree of freedom. So here let's think about it. Last class we have mentioned an example, this one, and we construct the contingency table for the research. Here we find that we divided the patients into two groups, with the drug and without the drug. And we divided the effectiveness into two groups, normal and a special disease. So this is a 2 times 2 contingency table. Sometimes we call it fourfold table, and sometimes we can call it 2 times 2 table. So here we can find that r equals to 2 and c equals to 2. So the df should be, yes, df should be 1. 2 minus 1 bracket times bracket 2 minus 1. So its df should be 1. So please remember that if we have a fourfold table, or I can say that if we have a 2 times 2 table, its corresponding df must be 1 in chi-square distribution. Okay. So next one, let's take an example. You can read it by yourself. Okay, I think you have already finished reading this, and next one I will show you the contingency table. And we have mentioned that last class in our examination, I won't give you this table directly, but I will tell you all the numbers in this question, in these words. So here if I show you all the numbers, you need to list all the numbers into the table. That means you need to construct the contingency table by yourself in our examination. So here, let's analyze the information which is given in this question. Here, we can find that we divided the individuals into two groups, yes and no. And we found that we have 4 age levels and the age. So here is a 2 times 4 contingency table. So here my question is, what is the DF in this question? Okay, I think you can do it right. DF is 2 times minus 1 times 4 minus 1, so DF equals to 3, right? Okay, so here this is 2 times 4 contingency table, and we can call it R times C contingency table. Okay, let's clean it. So here we want to identify, is there any significant difference between the two groups? So we need to use the chi-square test. Okay, so here let's watch the procedure of the chi-square test. So it's still step 1, step 2, step 3, and the conclusion. So here in step 1, we need to establish 2 statements of hypothesis. We have mentioned that for many times before. H0 means there is no difference of frequency distribution between the two groups with and without chest pain. HA, the alternative hypothesis, is there is significant difference of frequency distribution between the two groups. Alpha is still two-sided 0.05. We have mentioned that in our medical statistic class, we won't talk about the test for one-sided. So here alpha means two-sided. Okay, so here we want to do the chi-square test. So you need to calculate the chi-square value, but we have mentioned that according to the formula for chi-square value, you need to use the expected frequency for each cell. But here, let's go back to this slide. In this question, what is given in the question is the number of observed frequency. So this is not expected frequency. And we have 1, 2, 3, 4, 5, 6, 7, 8. We have 8 cells in this R times C table. So we need to calculate the expected frequencies for each cell. Okay, so here, in this table is the number of the expected frequencies. And how can we get that number? Let's go back to this slide. For example, for the 011 cell. So what's the meaning of 011? Do you remember that? We have mentioned that last class. Most often, we use OIJ to represent the observed frequency in the ith row and jth column. So 011 means in the first row and the first column. So this column should be 012, and this one should be 022, and the last one is 024. That's right? Okay, so here, let's clean it. For 011, the expected for 011, we can use E11 to represent its corresponding expected frequency. And we have mentioned that the expected for a special cell we need to use its corresponding row total times its column total divided by the total sample size, right? So we can find that this cell is in the first row, so its corresponding row total is 34 times its column total. This cell locates in the first column, so its column total is 74 divided by the total sample size is here in the right corner. That is the little n, and that is also the summation of all the 8 cells. Okay, so it's divided by 259. So this is the E11, and next one we need to calculate E12. So we can use the same way. 34 times its corresponding column total, that is 78 divided by 259. And E, we choose another cell, for example this one, E23. We can use its row total, 225 times 62 divided by 259. Okay, so here we just calculate the expected frequency for 3 cells, but you need to finish all of the 8 cells because you need all of these numbers to calculate the chi-square value. Okay, so here in this slide is all the expected frequencies I have calculated. I calculated all these numbers in the way we have mentioned just now. So we get all of these numbers. And then you can use the formula for chi-square value to get the test statistic. So here, for each cell, we need to calculate this number. We need to use the observed frequency minus its expected frequency for each cell, and then square it, and then divided by its expected frequency. So for 011, we can find that the number is 15, that is its observed frequency, minus 9.7, that is its E11, and square it divided by 9.7. So we need to calculate 8 numbers and sum them up. And then we can get the test statistic. So its number is 4.839. And the DF, we have mentioned that for a 2 times 2 table, the DF should be 1. But here we have a 2 times 4 table, so DF is 3. And then similar ways what happened in the other hypothesis test. Now we need to compare this number of test statistic with another critical value or another standard value. So that should be a critical value in chi-square distribution. And how can we get that critical value? We need to use a special table. So that is table A5. I think we have mentioned this table in last class in rank sum test. Okay, so now let's go to our textbook and find table A5. Table A5 is on your page 157. So let's read the title. The title is critical value. The critical value for the chi-square distribution. So we can find that this is a table for chi-square value. is table A5, and we can find that in the first column is the DF. So that means if you want to find the correct value, you need to find the DF firstly. So here in this question we find that the DF equals to 3. So we need to find the number from this row. And next one, we can find that in the first row is P. Actually, in hypothesis test, this P should be alpha, is equals to alpha, which is the significance level. And here, in our hypothesis of chi-square test, in the first step, we have established the alpha equals to 0.05. So let's find 0.05 is here. Okay, so here in the cross position, we can find that this number is 7.81. So here, this is the correct value for the chi-square distribution when df equals to 3, and we need to compare our chi-square value with this number. Okay, let's go back to our slide. Here we find that what we have calculated with the data given in the question is 4.839, and what we get from the table, the correct value is 7.81. So here this number is less than 7.81. So that means its corresponding P is bigger than alpha, 0.05. So can we reject H0? No, we can't. We cannot reject H0 because P is bigger than alpha. Okay, so the conclusion, because we don't reject H0, so the conclusion should be there is no significant difference among the 4 H groups. But I think this conclusion is not very exactly correct. I think it should be said there is no significant difference of the 4 H groups between the two groups, and we said that the two groups means yes and no, with or and without chest pain between these two groups. Okay, so this is the chi-square test for R times C contingency table. Next one, I will introduce you a special chi-square test. That is the chi-square test for four-fold contingency table, and we can also call it 2 times 2 contingency table. So maybe some of you will think that, oh, we have already known the chi-square test for R times C contingency table. So here this one should be the same or more easier than the R times C, because here we have 2 rows and 2 columns. We have quite a few cells in the contingency table. Yes, that's right. But please notice that there will be something special in chi-square test for 2 times 2 contingency table. For example, we need to learn the corrected formula. The corrected formula used in four-fold contingency table, and then we will learn a new formula for chi-square value in four-fold table. Okay, so here, when both variables in R times C contingency table have 2 categories respectively, the table is called a four-fold table or a 2 times 2 table. So here in this slide, this table shows the observed frequencies in the 4 cells corresponding to each row or column combination. The 4 marginal totals and the overall totals. So the marginal totals means 2 row totals and 2 column totals, and the overall total is here, the little n. Okay, we have already know we can use the formula for chi-square value to get the test statistic, but I wanted to say that formula we have already know is only the general formula for R times C table. So that means if you can assure that the question needs the chi-square test to solve, and you can use that formula. We need to learn 3 types of chi-square tests in chapter 8, and the general formula can be used in each one of the 3 types, but we can change it in an easier way. We can change the formula into an easier formula. Now let's replace the observed frequency with characters. We have mentioned that last week. For example, we use A to replace 011, B for 012, and C and D. With these 4 numbers, these 4 observed frequencies, we can calculate all the marginal totals and the overall total by using these 4 symbols. So here the 2 row totals are A plus B and C plus D respectively, and the column totals are A plus C and B plus D respectively, and the overall total is A plus B plus C plus D, and that equals to little n. And here we notice that in this fourfold table, we have 2 groups, and the grouping is based on the characteristics in the research. And here we use present and absent as the column, the 2 levels of the column. So here, if we want to calculate the present proportion in each group, we can get these numbers. For group 1, the present proportion is A divided by its total, A plus B. And for group 2, that is C divided by C plus D. And for the total, the present proportion should be A plus C over N. We have mentioned that in chi-square test, we establish the H0. There is no difference of the frequency distribution among the 2 groups. That actually means these 3 numbers are the same, and then we can use this number to represent the other 2 and get the expected frequency. That is what we explained last class. But here we can find that. Let's clean it first. We said that the general formula for chi-square value is sigma O minus E square over E. And we said that here we use the 4 characters to represent that O, and we can calculate E for each cell. For example, for the 011, E11 equals to A plus B times A plus C divided by N, and we said that N is the summation of A, B, C, and D. And you can find that Actually, we can use A, B, C, and D, these 4 characters, to represent the expected frequency. And also, we can use the 4 characters to replace the O. So if we put A, B, C, and D, these 4 characters, into the general formula, we can get another new formula. So it's here. Some of you will think that, oh, this formula is so confused. It's complex, right? It's complex than the general formula. But please believe that this formula, it seemed so confused, but in our calculation, this formula is easier than the general formula. Why? Do you notice that? In the general formula, we need to calculate the expected frequency for each cell. But here, in this new formula, we don't need to do that anymore, right? Because A, B, C, and D are all observed frequencies in the table. So all of the numbers are shown in the table. So you do need to calculate the expected frequency. However, here I want to say, actually, we still need to calculate some special expected frequencies because the formula for chi-square value has some special preconditions. But I will explain that later. Actually, you do need to calculate all of the 4 expected frequencies. You need to calculate only one. So here we can find that the calculation by using this new formula is very easy is easier than the general formula. And we can find that these 2 formulas, they are equal. So you can choose either one. But I think you'd better use the new one if you met a 4-fold table, because this one is easier for the calculation. But please notice that the formula we have learned before is the general formula. That means this formula can be used in each type of the chi-square tests. But here, the new one must be used in 2 times 2 table. It can't be used in R times C. That means when the rows or the columns are more than 2, you cannot use this new formula anymore. So you can call it a special formula for 4-fold table. And df is the same, R minus 1 times C minus 1. But we have mentioned that no matter for the general formula and the new formula, it has some special preconditions. The chi-square is an approximate method which based on the normal approximation to the binomial. A conservative rule for the validity of the chi-square calculation is that the expected frequency in each category be at least 5, especially for a 4-fold table. So if the rule is not satisfied in a 4-fold table, there is the need for a continuity correction. But actually, here we have 2 preconditions. The first one is the expected frequency of each cell must be at least 5. So E ij must be more than or equal to 5. This is the first precondition, but we still have the second one. The second one should be the overall total, the little n should be bigger than or more than 40. So that is the two preconditions for the general or the new formula. You need to remember this. You need to remember this precondition and its corresponding formula. You need to remember the formula here. But the appropriate continuity modification consists of reducing the absolute magnitude of observed frequency minus expected frequency by a half. So that is how can we calculate the general formula. So here the general formula becomes this one. So you need to notice that this formula is used when its corresponding expected frequency. Let's clean it. This formula should be used when we found expected frequency for a cell is less than 5 but more than or equal to 1, and n is bigger or equal to 40. We can use this correction formula. So it's the same in the new formula. When the precondition is not satisfied, we need to correct the new formula. So that means the new formula has the same preconditions. When E for a cell is less than 5 or and more than or equal to 1, and n is bigger than or equal to 40, we can use the corrected new formula. And here let's watch what is the corrected formula. So here for the general formula, this is the corrected one. We can find that we use the absolute value of the difference of observed and expected frequency, and then minus 0.5, and then square it divided by expected frequency. If we use the new formula, and when the rule is not satisfied, we need to calculate this formula AD minus BC and calculate its absolute value, and then minus half of n. The other parts are the same with the new formula. Okay. df, the formula for df is the same, r minus 1 times c minus 1. So this is the corrected formula for 2 times 2 table. Here I want to explain further. Let's clean it. Please notice that for each formula we have two preconditions. For the formula without correction, we need t is more than or equal to 5, and not t, is e, and n is more than or equal to 40. But here please notice that e means all of the 4 expected frequencies. That means all of the expected frequencies must be more than 5, and n must be more than or equal to 40. And this time you can use the formula without correction. And here, the corrected formula is used when E is less than 5 and more than or equal to 1, and N is bigger than or equal to 40. So here we can find that it's still two preconditions, but this one, E, that means there is at least one cell has the expected frequency which is less than 5 or equal to or more than or equal to 1. So we don't need all of the 4 expected frequencies are all less than 5 and more than or equal to 1. We need at least 1. So if there is at least one cell has an expected frequency like this, in this range, we need to use the corrected formula. So here, I have mentioned that for the four-fold table, you don't need to use the general formula. You can use the new formula because you don't need to calculate all the expected frequency. But here, because of the preconditions, because of the rule, you need to calculate at least one expected frequency. But please notice that I mean only one, not all of the 4. So which one do we need to calculate? Let's clean it. Here we said that in a four-fold table we have group 1, group 2, and present, absent 2 levels. Here is A, B, C, and D. So here we need to calculate only one expected frequency. So which one? We need to calculate the smallest one. That means the mean of the expected frequency. But how can we know which one is the smallest? We have 4 expected, right? Because we have 4 cells in this table. So there are 4 expected frequencies. So how can we know which one is the smallest? Let's think about the formula for expected frequency. That is the row total times its column total divided by n, the summation of the 4 observed frequencies. So here we noticed that for the 4 expected frequencies, all of them had the same sample size denominator, right? They have the same denominators, but their numerators are not the same. So who has the smallest numerators? That one is the smallest expected frequency, right? And we can find that this is the product of row total and the column total. It's the product of row total and the column total. So that means which cell has the smallest row total and the smallest column total? It must have the smallest expected frequency, right? Okay, so here in the true row total, this is RT1, RT2, the row total. So we need to compare these two numbers. Which one is smaller? For example, if RT1 is smaller, that means the smallest expected frequency must locate in this row. And let's clean this part. If we find that in the true column total, CT1 and CT2, if we find that this number is smaller in these two numbers, CT1 and CT2, that means the smallest expected frequency must locate in this column. So we can find that the cross position is the first row and the second column. So this cell must have the smallest expected frequency. So we can know that its expected frequency equal to A plus B times B plus D divided by N. Okay, so please notice that which cell has the smallest expected frequency is not related with the number of the observed frequency. So that means the smallest observed frequency maybe doesn't have the smallest expected frequency, because expected frequency is depend on the row total and the column total. It doesn't depend on the number of observed frequency. Okay, now we have already know how to calculate the expected frequency, the smallest expected frequency. Now let's take a break.